So good morning, everyone, or good afternoon, or good evening, depending where you are. Today's webinar, which is the 11th webinar, will be on diamonds. It will be something out of the box because it's not a technical webinar on diamonds. And it has a little bit of history, a little bit of technical things, a little bit of geology, a little bit of mineralogy. So it will be a mix of informations about one of the most famous, if not the most famous gemstone of all, which is diamonds. So I always say the same joke. Hopefully I will share the right one. So I still have a couple of slides. Those were design options. So what are the topics for today? I will address a little bit about the value of diamonds. I'm not saying how much they're worth, but we will discuss a little bit of value, curious things about the value of a diamond. Also, what is a diamond? Or what is it as a material? Don't go much into the mineralogy, but it's really interesting to understand actually what it is. And it's impossible not to give you a few geological curiosities about diamond because it's really unique as a geological material, and also some historical curiosities because the use of diamond goes back in history, and some diamonds have rather interesting stories that go along with them. And also we will discuss two trade terms that usually are associated with diamonds. One is Golconda, the other one is Cape. So we will talk about that one. We will also address, now everybody wants to have a type 2A diamond, and we will explain really in brief what's a type 2A diamond and why are they so valuable. And at the end, because we were discussing color descriptors like Golconda and Cape, and I mean not type 2As, because type 2As, they can be colorless browns or sometimes pink. We'll discuss just a little bit of color grading and how it's done. So pretty much like that. I won't be talking, I mean, I announced, and I'm so sorry, I did announce that I would speak about synthetics, which today they are called lab grown, but they are synthetic artificial products. So synthetic diamonds I won't address today, and also treatments and also identification, because GIA channel, they did a terrific job, and you can listen to this presentation by Mark Breeding, which covers pretty much all the important aspects about synthetic diamonds today. Really well, really great presentation. Make sure you visit the GIA channel and check it out only after this webinar, of course. So value, this is interesting. You are seeing here Johan holding up 500 carat plus diamond. It sold for $35 million almost 10 years ago. It came from the Cullinan mine. So we are discussing how concentrated is value on a diamond. Let's discuss a few materials. This is silver. Do you know how much it costs 1 kilogram of silver? And I'm sorry, those numbers are from yesterday, I think, not today, but it doesn't matter. So it's about $500 a kilo of silver. Do you know what this is? Saffron. You can use it to make yellow rice. Like when you use chromium, you can have a colorless corundum and turn it red. In rice, you can have saffron and you can turn it yellow. And saffron can be very expensive. And 1 kilogram of saffron can be $15,000 plus a kilo. So go figure that out. And of course, caviar, I would die for a nice caviar. Very good caviar costs more than $20,000 a kilo. And platinum. Platinum used to be like, wow, really expensive. Not anymore red compared to gold, because 1 kilogram of platinum, it's about $25,000. And of course, gold. 1 kilo of gold is $55,000 today. It's crazy. It's going crazy. And you know, I'm holding on my hand. That's 1 kilo of gold, of pure gold, and 4 nines gold, 999.9 per thousand, pure fineness. And you can hold a BMW here on your hand. So that's how concentrated gold is. And you see here these few chaps, myself and a few friends that I've shared a really nice travel in South Africa, and we are looking at $20 million of gold. And so we don't have that many bars. It's 36 bars of gold. And Jean-Pierre Chalin, he's a very famous diamond expert. He works in Switzerland, so he's maybe figuring out how can he bring that up to Switzerland. This was on the Rand refinery. It was a great trip, and we didn't take anything with us. Now, really expensive. Do you know how much it costs? 1 kilogram of plutonium, about $4 million, 1 kilogram of plutonium. More expensive than plutonium by the kilo, it's, my dear Cristiano Ronaldo, about $5 million a kilo if he doesn't get fat. So that's about his net value today. But we are talking about diamonds. And diamonds, they are sold by the carat, not by the kilo. So I'm going to go into a very demagogic kind of rhetoric to demonstrate to you that diamonds are really, really valuable. So diamonds are sold by the carat. 1 carat is equivalent to 200 milligrams, which is 0.2 gram. And it has been like that since 1907. So more than 100 years ago, it was defined that 1 carat equals 200 milligrams. Therefore, in 1 gram, you have 5 carats. And let's take a look on this fabulous, outstanding, the fancy blue diamond, the Blue Moon of Josephine. It was sold a couple of years ago by almost $15 million, making it, up until now, the most expensive diamond by carat value, which is approximately $4 million a carat. And do you remember Eloise Gaillou? She joined us a couple of webinars ago, talking about fancy colored diamonds, and she's holding $50 million. You see, $50 million like this. So if we convert it to grams, it's about $20 million a gram. By the kilo, $20 billion a kilo. Okay, 20, in Portugal, a billion is a million of a million, but let's make it easier. $20 billion a kilogram. And do you know where can you store, what's the volume, approximate volume of 1 kilogram of diamonds? It's a beer can. So if you have a normal beer can, that's 1 kilo. By the way, that's a really nice Portuguese beer. If you travel, you can try this one. We have Sagres also. I don't want to, they are not paying me anything, but they should. Even a regular engagement ring, like a $50,000 engagement ring, and a really nice one, by the way, you can have a diamond there that costs $20,000 a carat. Even so, we are not talking about the blue, very expensive blue diamonds. We don't find 1 kilo of those diamonds, do we? It's really rare. But even so, a really nice diamond for an engagement ring, we can be talking about $100 million a kilogram. So diamond actually holds the most concentrated value on the planet. Nothing is more expensive, nothing values more by the unit of weight than diamond. And diamond is only carbon, normal carbon. And everybody knows carbon because of climate change, of the greenhouse gas, that fortunately, because of the COVID-19, the planet is breathing a little bit better, but carbon, it's a problem. But carbon is also great because carbon makes part of forests. So we also know that forests and trees, they capture carbon. What most people forget, but we geologists, we know that carbon is also part of many rocks. And one of the rocks that has carbon a lot, so pardon my English, it's the limestone marbles, which are kind of I don't want to say funny words, metamorphosed limestone, which is limestone that was transformed, which is basically the same thing. You have a lot of carbon in here. By the way, this is the Palácio de Mafra in Portugal. It was built because Portugal had money from the gold and diamonds from Brazil. So that was, this is also related to the jewelry industry, the money that was raised to pay for this monastery. Great monastery. I did my military service in there. It's also for militaries. Archaeologists also take advantage of carbon to do radiocarbon dating. So even it actually can be done on corals and on pearls today, the radiocarbon dating. So we hear about carbon everywhere. But mineralogists, they know that there are also some minerals, not only diamonds, that have carbon. And I'm going to show you just a few that can be used as gem materials: rhodochrosite, manganese carbonate, malachite, copper carbonate, calcite, calcium carbonate. And of course, every precious coral is made of biomineralized calcium carbonate. Also, shell and mother of pearl is made up of biomineralized calcium carbonate, everything with carbon. And of course, natural pearls and cultured pearls as the same. So carbon is around us everywhere, even in jewelry, but especially on diamonds. And what does it make diamonds so special? Because every carbon atoms, they don't like to be with each other. Maybe as many of us, if we are in small apartments with big families, everybody together, imagine the tension. So carbons, they hate to be close together with each other. They like to be at ease. But if they are pressured, they must be together. And in terms of crystallography, I don't want to bore you to death with crystallography, but carbon atoms in diamonds, they are close together in a very special arrangement that we call them in the cubic symmetry arrangement, tetragonal things. There is another form of carbon that we use every day in pencils, which is graphite. Look at the name of the mineral, graphite. Graphos in Greek means writing, right? So calligraphy, orthography, graphy, it has all to do with the stone. So they named this mineral because it was the rock that could write. That's why it has that name. And it is, you can write with that mineral because the connections, the bondings between the atoms are not as strong as with diamonds. So a little pressure will make that bond to break. And that's why you can leave little bits of graphite when you write on the paper, as you see in there. So those two chaps, they are carbon. But in diamonds, carbons are really pressed to each other. They hate it, but they have to. In graphite, oh, they are much more relaxed. It's much more at ease. And I don't want to say funny words, but in mineralogy, we call it polymorphism. Actually, in native elements, like when a formula of one mineral is only one element, we call it a native element. We call them allotropes. So now you can go to your dinner party in the evening, and you can, at the table, you can say that you learn a new word, allotrope, because graphite and diamond, they are allotropes of carbon. We find it very interesting, maybe you don't, but allotrope you won't forget for sure. And the difference is diamond is an allotrope of carbon that is under pressure and high temperature, and graphite low pressure and low temperature. So that shows you that in nature, depending on the conditions of formation, the same chemistry can have different shapes, different kinds of shapes. The same with cooking. You have the same ingredients, you cook them differently, or you burn everything and you have different tastes. So there you go. Now a little bit of geology. Why does diamond have that kind, why do carbons connect with each other in such a way? Because in the planet, they are formed in really great depths. Down 150 kilometers below, up to 700, 750 kilometers below. That's where carbons, the poor chaps, they have to be, they are pressed within each other. I don't know if you have dived, you have made any diving, but you know that when you dive, the pressure goes up. And if you dive to 30 meters, you have a lot of pressure in your ears. Imagine the poor carbons at 150 kilometers of rock on top of them. It's enormous pressure. So that's why diamonds can form. Also, there is only pressure equivalent to 14,000 the atmospheric pressure, but also really high temperatures. And when you have these conditions under what geologists call the cratons, I'm not going to explain it, then you can have the conditions to form a diamond. If you go on Google and look into that gentleman, Fabrizio Nestolla, he's a diamond geologist, a great speaker. He gave a presentation at GEM-A conference last year. It was brilliant. He makes geology so easy and fascinating that you want to become a geologist after you listen to Fabrizio. And he explains how does carbon, how come we have diamonds? And it's because of Fabrizio that I learned that, by the way, bridgemanite is the most abundant mineral on the planet. It's all over the mantle, you have bridgemanite, but this is outside of the story. If you go also to GIA YouTube channel, check out this Evan Smith presentation on the geology of diamond. He's also a great speaker. It's about 50 minutes presentation. You won't regret. And he explained it, the geology, in a very, very organized way. Go there and check it only after this is finished. So, of course, if diamonds are formed in such great depths, is man going into those great depths to fetch them? This is one of the largest diamond mines on the planet. It's in Siberia, so you can have a look. This looks like a Star Wars kind of scale. It's huge hole on the surface, but this hole is about 600 meters deep. And you remember that diamonds are formed in greater depths. Also, when you have underground operations, they hardly go below 1,000 meters. So, I mean, how can we reach diamonds? I mean, we don't reach diamonds where they live and where they are formed, and where they still are. If we could dive 200 kilometers below cratons, I'm sure that we would find rocks with a lot of diamonds, and some could be like, wow, big ones. What happens is those diamonds were brought to surface by a volcano, and that volcano has a name. It's a kimberlite-type volcano. We have more types of volcanic things. We have lamproite and lamprophyres, but this is beyond the point. I just want to focus on kimberlite. It's a really violent volcano. Do you remember when I said that carbon atoms, they hate to be with each other? Imagine if the volcano was like slow coming from 200 kilometers up, they would have enough time to, upon the release of pressure, they would say, okay, now I don't want to be with you, and they would transform into graphite. But because the eruption is so fast, and when I say fast, it's really fast, and it's like an explosion, then the poor carbons, they have no chance of separating each other, and they come to surface brought by that magmatic material called kimberlite. And they came to surface and they remain as diamonds forever. Not forever if you don't treat them right. Julia Griffith actually has a great video on her YouTube channel explaining are diamonds forever. So she explains quite well what you should avoid when you have a diamond. Don't hammer it, don't burn it, things like that. So, and just interestingly, our planet had kimberlitic activity, meaning we had that kind of really violent volcanoes up until for 500 million years, up until 50 million years ago. There haven't been eruptions like that in 50 million years. Do you remember, I always tell this to my students, do you remember Cristiano Ronaldo when he started football? He was 17 years old. He had, I don't know how to say in English, those things that adolescents have on their face when because of the hormones. When you look at him now, he's an adult, he's 35 or something. He doesn't have those things anymore because the hormones are different. Pretty much same with the planet. The planet had a lot of hormones like 200, 300 million years ago. Now the planet is a bit more older, so not that kind of volcanism anymore. I know that some geologists, they are looking at me and say, oh, he's comparing geology with those red things. I don't know the name. I'm sure somebody will tell me on the chat. But we know that kimberlitic eruptions also happened in much older times. Interestingly, we have diamonds that are older than 3.5 billion years. For those of you that are geologists, you are used to what is a million years. But for those of you that don't know, a million years is the geologist's scale. We, in our lives, now we measure time by the day, one more day of confinement. But geologists, they measure time at millions. And if you want to know what a million year is, 1 million years is about 10,000 centuries. 10,000 centuries a lot. But if you want to really know what a million is, you are at home, you are locked down, so you grab some rice and you grab 16 kilos of rice, or just grab one and use it 16 times. And then, because you have nothing to do, for 8 hours a day, you will count 1 grain of rice each second, and you will take about 1.5 working days, 8 hours a day, 1 grain per second, to count 1 million grains of rice. And you need 16 kilos approximately of rice to do that job. Maybe the confinement will be over and you will still be counting rice. So if you are on sales and if you are selling a $1 million ring to a client, if he wants to pay cash, make sure it's not $1 bills. Otherwise, you will count it for a month or more. So just to give you an idea what a million is. Interestingly, but that was just a curiosity, intellectual curiosity, if you wish. But diamonds, some of them are so old, they are as old as 2/3 of the age of the planet, and our planet is quite old. Do you remember Carl Sagan? And he had that brilliant series, Cosmos. And I remember he had this cosmic calendar where the 1st of January was the Big Bang, the beginning of known universe, and the 31st of December, midnight, would be today. So let me just present you his calendar related to diamonds. So Big Bang was about January the 1st. Our galaxy is in March. Our planet or the solar system is September 2. Life on the planet, life, as we know, it's about 3.8 billion years. So September. The extinction of dinosaurs, that it was so long ago, was already in December. And we, man, the species that is doing these things to the planet, we just arrived here, okay, 2.5 million years ago. And if in the calendar is about 10:30, December 31st. So when we are in New Year's Eve, we are having dinner. And the common era, so when we start the Gregorian calendar, started, look at it, 5 seconds to midnight. And this is just to show our relevance in the universe. Is nothing. But diamonds on the planet, they were about at the same time as life. So diamonds actually are older than dinosaurs, older than, it's almost when life appeared on the planet, the first diamonds also appeared on the planet. For those of you that like poetry, maybe you can think a few things, life, diamonds, blah, 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 blah. That's it. But this is interesting. So diamond is a unique mineral because it has a unique composition, only carbon, has a unique geological formation. down at the great depths in certain areas of the planet, and it can be also very old. But this is not what makes diamonds so special as a material. What makes it so special is the properties. It's the hardest natural material that we know. It has the biggest thermal conductivity in the materials, great sound conductivity as well. It's chemically inert. You cannot, it's really hard to chemically degrade a diamond. So that's why diamonds have been fabricated, manufactured for decades for industrial purposes. Now we know that they are also being manufactured cost effectively for the jewelry industry, but for decades, diamonds have been manufactured for the industry. Of course, when you have a natural diamond and when we polish it, then we have all those visual properties that everybody likes, like brilliance, scintillation, and fire. And actually, it's really beautiful when you look at a well-cut diamond. It's really breathtaking if you care to be touched by that beauty, especially under candlelight. But that diamonds, before they are cut, they are not that special. I mean, they are nice crystals, but they are not that special. Curiously, in the old times, diamonds were not used in jewelry as fashion materials. They are not fashion. They were not cut. They were used as this is, as crystals, because cutting of diamonds, and the diamonds were first found in India, also a little bit later in Borneo, Indonesia, but mostly in India. They were used in jewelry, as you see on your screen. The crystals themselves, they were being used as it is because diamond was so hard that technology didn't allow to polish them as we know that they can be polished today. Everything changed then in Europe because of the Portuguese, of course. Diamonds were manufactured and polished before the Portuguese started to bring diamonds directly from India, Goa, to Portugal in Lisbon. But the whole trade of diamonds changed because of the gentleman Vasco da Gama. And when we established the commercial trading post in Goa, Goa became like the center of luxury in precious stones in Asia. And diamonds were reaching Goa from Golconda, I will explain what it is, and also Vijayanagar, I don't know how to pronounce it correctly, but in Portugal we say it Bijnagar. It was two areas in India that produced diamonds. They were actually really active, and those diamonds were then brought to Europe after the 16th century by the Portuguese. And cutting was being evolved, and one of the first cuts was the so-called point cut. And point cut, if you look at it, it's nothing more or really similar than the octahedral crystal shape of a diamond, the same shape that you just saw on the slides before. So this was one of the first ways of fashioning a diamond, and it was so visually impactant, and diamonds were so special because they were hard to cut, that diamonds, the notion of a diamond was something that also in architecture was really important. Those of you that are from Italy, you know the Palazzo di Diamante, but this is in Lisbon, and this is in Casa dos Bicos, House of Spines. I don't know how to translate it. It's English. It's a house built in 1528. And if you come here and you look at this, when you look at this, you are looking into diamonds. Not diamonds, they are limestone, but as diamonds, as point cut diamonds. The other kind of cut that you can also see in other decorative arts other than jewelry is the table cut. Table cut is pretty much a point cut where you just cut one of the points and then you have a table, what we call the table facet. And we can see that actually in tiles, azulejo in Portuguese. You can see in many parts of Lisbon. This one was taken in Museu de São Roque, which is right in the center of the capital. And you can see here, let me just, I think you can see my mouse. You can see here a point cut diamond. And next you see table cut diamond. So when you look at those styles, you are looking at diamonds. And in Portuguese, we call them padrão ponta de diamante, which means pattern in pointed diamonds. Really, really nice. They were made actually in southern Spain, really popular in Portugal. And this takes us to Indian diamonds, because India was the most productive area of diamond production back in the 16th century and even before. And one of the most famous Indian diamonds is the Kohinoor. And the Kohinoor that resides today at the Tower of London since 1851, that actually is in London. But before that, and before it had this brilliant cut shape, it had another kind of shape that you can call it a mogul cut, like you see here in a model that was shown a couple of years ago on an exhibition, showing the two stones, the before when it was fashioned in the 16th century, and after when it was recut by Costa Diamonds in the 19th century. And it was really a big, huge stone. It was a 191 carat stone. When you look at the literature, you see a lower value, but that lower value are old carats, not new carats. And that diamond, there is a nice story about that diamond, because people, when we look at books, we say that it was named Kohinoor, and actually before that, some people called them the Babur diamond. Babur was the first Mughal emperor, but there is no evidence that it actually belonged to Babur, but it doesn't matter. But when this diamond was in India, and when the Persians conquered Delhi, there is this story that Muhammad Shah, he had a turban and he was hiding the diamond in his turban. And when Nadir Shah of Persia, they say traditionally they had to swap turbans. And when he opened the turban, he looked at the diamond and said, Kohinoor, that is something like mountain of light. But that is kind of a story, because on a peer-reviewed article published not that long ago, it is advocated that actually Kohinoor stands for mountain, and it was named like that because it looks like a mountain, the cut looks like a mountain. And that story between the turbans, that's just a story. But I mean, diamonds are full of stories, and that's fascinating. So if you look, I think it was published at the Journal of Gemmology, which is the GEMA peer-reviewed magazine, and look at the Gems and Gemmology Journal of Gemmology archives, and you can look for this article. Quite interesting. But most important when we talk about diamonds is Golconda, because Golconda, we are associate Golconda diamonds with really, really expensive and unique diamonds. And what is Golconda? Golconda actually is a fortress, is a citadel in Hyderabad in India, that many years ago had this fortress, but there were no mines, no diamond mines around Golconda. Around Golconda, you had diamond mines about 250 kilometers southeast of the citadel, in a place called Kollur. So around Kollur, you did have alluvial diamonds, and when the Kollur area had mines. Golconda, no mines. So when you see Golconda mines, it's nothing. It's wrong, because Golconda was only a fortress where diamonds probably were kept, but not. There is no single diamond mine in Golconda itself. They are really far away. And from Golconda, of course, from the Golconda area, or from the Kollur area, or around Golconda, if you wish, really famous diamonds actually were fished. Not fished, they were caught. They were, I'm missing the English word. They were mined. And this is one of the most famous ones. It was presented to the King of France by Jean-Baptiste Tavernier. It was cut into the French blue, which was a 69 carat blue diamond on the French crown jewels. Then during the French Revolution, the diamond was stolen. And then by chance, it appeared on the market as this 145 carat stone. And it has a fabulous story. It was bought by John Henry Philip Hope, and then today is at the Smithsonian. Curiously, we saw Héloïse Gaillou, French, working at the Smithsonian and studying this diamond. When I learned that she was going there, I thought that she could be like French Secret Service, going to the Smithsonian to try to bring back the Hope diamond back to France, but it didn't happen. More diamonds from Golconda. You have the Witzelbach graph. It was recently recut. It was originally a 35 carat stone. As you can see here on this image, it was recut by Graf into a 31 carat stone with a better polish and better color. Also a Golconda stone. Another one in colorless category, you have the Régent, the Regent diamond in the Louvre. It's closed, but you can go into the Louvre website and you can see the picture and the description. It was cut from a 400 carat diamond from that area, from the Golconda area. We know that Golconda is not a mine, so from the Golconda area. And it's currently on the Galerie d'Apollon, and it's next, by the way, next to the Hortensia diamond and to the Sancy diamond. And you see here a really nice spinel. And of many other. I could be here almost forever showing you Golconda diamonds. This is Archduke Joseph diamond, a quite nice D-color, meaning totally colorless, IF meaning internally flawless, with you cannot see nothing inside, with a 10-time loop, so it's a perfect diamond. Also Golconda. But you also have Golconda diamonds that are either blue, completely white. You also have slightly brownish ones, like the Sancy that was sold recently for $9 million. And this is quite, it's a K color, faint brown stone. Nevertheless, $9 million. Wow, it's a really, and look at the cut. It's a double rose cut, quite rare to see today something like that. But Golconda, or India, or that area of Golconda, they did produce not only the woo la la fancy shapes or fancy colored diamonds and really colorless special diamonds. They also produced the normal ones, the little ones, the normal gem quality diamonds that you see on jewelry. And these are nice examples of 16th century and 17th century jewelry from the Albion Art Institute, using diamonds that, if they are of this age, they almost certainly are from India, and from India they possibly are from the Kollur or from the Kollur or Golconda area. So Golconda, it's not like synonymous of, oh, everything that comes from Golconda is like ooh la la. No, these are normal diamonds. They came probably also, and all of the diamonds that you can see on 14th century, 16th century, 15th century, 17th century jewelry before Brazil came into action, almost all of them are from Brazil, or sorry, from India, some from Borneo, of course, and in India, most of them would come from Golconda, also from other areas. But today, you see a lot, especially in auction houses, and also from manufacturers. This is a really nice Cartier late 1980s ring by Cartier, that it was sold as a Golconda diamond, because Golconda was associated with a certain type of quality. And today, some gem labs like Gublin Lab or SSEF, if they issue a Golconda appendix, which is when a stone is really special, you need to follow certain rules, but the stones are not necessarily from the Golconda area. So pay attention, because when you see Golconda today or Golconda type, it doesn't mean that the stone comes from India. It does mean that the stone is a type 2A. We'll see about that later on. That the stone is D-colored, so totally colorless. That the stone is internally flawless or potentially internally flawless, or even flawless. So it's nothing inside of that you can see with 10 times magnification. Also, it has a special transparency, a special crystallinity. It has to do with graining. It's really special that when you look at a D-color IF stone, a Golconda type and a non-Golconda type, they look different. There is something special with them, and it has to do with graining. And if those labs are to issue that appendix, stones must be above 4 carats, and the cut must be an antique, or originally an antique cut. Some say below, not below, before 1920s, but it should be old, even with some wear marks. You can repolish, but then you resubmit the stone to the lab, and you have the same appendix with the Golconda or Golconda type. And here you can see a nice example from a Cartier ring. So Golconda is not, it's not necessarily an Indian, old Indian stone, and make note of that, because that's important. Another word, maybe the young people don't know this, but the older people like myself and some of you in the audience, you remember talking about Cape diamonds. Well, Cape diamonds, you call those diamonds Cape not because of Cape Town. And by the way, Cape Town, if you go to Cape Town, the first guy, European guy, to visit Cape Town was a Portuguese, Bartolomeu Dias. And near the Sheraton, you have a statue of my compatriot Bartolomeu Dias over there. He was the really first one to go around the Good Hope cable. But that's patriotism. But you call them Cape diamonds because of the British Cape colony. That Cape Town was the capital, but it was because of that territory, not because of Cape Town. And in 1866, in the Kimberley area, diamonds were found, and they were found in many areas around the area, You understood. And because the many of those mines, they were producing stones of different colors, and because they sometimes stones from one mine were characteristic, had a few characteristics, and stones from other mines had other characteristics. A lot of trade names of color descriptors related to mining were being used in the trade in the late 18th century. And the word Cape was related to slightly tinted yellow stones like this one that you see on your screen. This is the Eureka diamond, the very first one found in South Africa. It's now part of the Kimberley Mine Museum. If you go there and visit the Big Hole, which is the mine, you can actually see the Eureka diamond that was bought by the South African government not that long ago. And so Cape is related to yellow stones. Even in the UK, because in Great Britain, you also have everything different. You have imperial units, you drive on the wrong side of the road, and also in nomenclature, you had different things. So those were the old nomenclature in the UK for diamonds, not necessarily the ones that were using mining names, but these were the ones. But Cape was also related to a yellow color. So whenever we hear the word, oh, a Cape diamond or a Cape series diamond, we are talking about diamonds with a perceptible yellowish tint. That's what Cape means. Because on the Cape colony, on the Kimberley area, most diamonds on the 19th century, they had this yellowish tint, which is normal in diamonds because most of them, they are type 1A. They have aggregated nitrogen, so they tend to be yellowish. Like this nice assortment that you see on your screen from De Beers. And you can see here a few less tinted and more tinted yellowish stones, among with some others. So when Cape relates to those yellowish stones that you see on your screen. And when you see finished jewelry, depending on the quality of your screen, you might not capture what I want to say, but look at the diamond in the bottom, the big one. You see a slightly tinted yellow tint, another redundancy. And this is what the Cape means, is this really light tinted thing that you see on diamonds. And to finish, and we are almost in the end, type 2A, because nowadays, even on some auction houses, you see, oh, type 2A, wow, type 2A. Type 2A is nothing special for a mineralogist. It just means that it is a diamond that has no nitrogen. In Portuguese, we say azoto, nitrogen, detectable under infrared spectroscopy. So with a machine, if you don't detect nitrogen, you call them a type 2A. So, but in plain words, means a chemically pure diamond with nothing. It's only carbon, nothing else. But as Eloise Gaillou explained in her presentation, and as you will see from Thomas Einschwang in a few hours, type 2As, they can be chemically pure, but if the atoms are like dislocated, if they have defects, then they can have color. But usually type 2As are related to D-color diamonds, so colors, the totally colorless diamonds, also to pink diamonds and to some brown diamonds, as Thomas Einschwang will explain in a couple of hours in his gemology webinar. And so another Portuguese treasure, Sara Sampaio, holding the huge Lesedi Larrona diamond that was found in Botswana not that long ago, the largest diamond ever found on our millennia, in our century. It was found as 1,109 carats after it was cleaned. And curiously, 1,000 carats is huge for a rough diamond. But scientists, they have discovered that other huge fragments that were found on the same mine, and Karoe mine, they were part of the same crystal that originally had possibly over 2,700 carats, that during the eruption it was broken. So what Sara Sampaio is holding is a fragment of a yet larger diamond that didn't reach, as the Cullinan diamond reached the surface, over 3,000 carats. This one was broken into several ones. The one, this is the most famous one, the Lesedi Larrona, but you have the other one, the Constellation diamond, 812 carat diamond, also really famous and cost a lot of money. It was Lawrence Kraft that bought this diamond, and it took a long time to decide what to do with that huge rough. And eventually it resulted in an over 300 carat D-color diamond that is called the Lesedi Larrona. It's cut on an Asher cut. It's like this. It's like like my diamond, but bigger than my diamond. So that's why, because of those really expensive and really unique, totally colorless diamonds, that when you hear type 2A, it's like, whoa, type 2A. But because diamond colors should be communicated in a very professional and consistent way, we have diamond grading systems, and we have systems for grading and classifying the color. And all started with this gentleman, Richard T. Liddicoat. He was president of the GIA. He passed away not long ago. I personally met him. He was a lovely man, really generous. And diamond grading actually began in the 40s, when the Beers were joining GIA in America after the Second World War, touring the United States, teaching retailers how to understand diamonds. Diamond grading started to be organized, and in 1953 the GIA came up with its grading system that is called International Diamond Grading System, that's still benchmark today for diamond grading all around the world. We have a lot of diamond grading systems, but actually GIA is the most famous one. And it's, I mean, we all know those characteristics, those 4 C's, but this is a 1949 working sheet that it was not called the 4 C's, it was called the 4 rules, because when we say the four C's, actually, it's not a grading system. There is no four C's grading system. Four C's were actually a mnemonic for students to remember: carat, cut, color, and clarity. That was a mnemonic, not a system. The system itself is International Diamond Grading System, and it's quite simple. I mean, it's just for color, it just measures the deviation from colorless that a certain sample has when it is yellow, gray, or brown. When the deviation is on three colors, you grade them on a D to Z scale. Everybody knows this. Those of you that work in the industry, you know this thing. And GIA uses 17 master stones, 17 patterns that you can see in here, and also color descriptors that, depending on where you are, you call them colorless, near colorless, faints, very light, or light. Note that after the color O, each master represents two colors, which is interesting. So 17 masters, 17 grades for GIA. When the color of the diamond is not yellow, usually GIA grades the stones with the letter D to Z, if it is within the D to Z, and then if it is more than K color, along with the letter, it also puts the color descriptor. Like, for instance, on this one, remember, the Beau-Sancy, it's a K color, but it's a faint brown. That's how GIA grades it. Of course, if the brown falls beyond the Z color, then we have a fancy. We have a fancy color. This is not actually a brown color, but I mean, talking about brownish stones, I couldn't miss sharing this one, which is the incomparable diamond, for more than 400 carats of diamond that Mawad, they built this necklace, and it was on sale a couple of years ago for $55 million. I don't know if they sold them or not, but it's a remarkable, huge stone. But if you want to see a real fancy brown one, this is a 100-carat, a pear-shaped diamond on a Cartier necklace. It's quite remarkable. I saw this one at Gem Genève last year. It's really remarkable. The color is eye-catching. It's quite, every big diamond is eye-catching. Because brown is not the most sexiest name, and Eloise, she talked about this on her webinar, they invented like this name, champagne, cognac, just because it's more romantic than the word brown. But if you want to learn everything about brown diamonds in exactly 2 hours and 5 minutes, log into the AIGS webinar and go to AIGS Thailand social media, which is mostly Facebook or the Instagram. Look for the link and join. Thomas is a great speaker. He's one of the biggest diamond specialists in the world. Biggest because he's tall, and biggest because he has a big intellect. He runs a research laboratory in Liechtenstein, and it's really worth listening to him on brown diamonds. And he will explain why diamonds are brown and what types of different kinds of browns and the mechanisms of making brown that you can listen. So make sure only after this webinar is over, look up for the AIGS webinar just in 2 hours and join it. I will be there as a student, so I will log in before, so you don't take my seat away from me. So it's really, and this is a technical webinar, not my own webinars are more blah, blah, blah. This is the real thing by the real experts. So in conclusion, and this is over, we mentioned that diamonds have the highest concentration of value on the planet and maybe on the universe, we don't know. It's a crystallized form of carbon, and every one of you will remember the word allotrope. Diamond is an allotrope of carbon. Diamond and graphite are allotropes of carbon. So you will never forget this is the same material. But diamond forms at great depths, usually under 150 kilometers, up to 700 kilometers, great pressure and great temperature. The geology is quite interesting, and some of them can be really very old. so old that can be as old as life on the planet itself. Older than the dinosaurs, almost all of them are older than or contemporary of dinosaurs. So that's also an interesting thing. Another one was Golconda. Golconda actually is a place in India, in the Andhra Pradesh, but it's not a mine. Golconda had never mines. The English. The Golconda never had any mine. What it was a fortress that probably the mines around Golconda, especially Kollur, 250 kilometers southeast of Golconda, maybe those diamonds went to Golconda, and from Golconda, possibly to Goa, from Goa, by the Portuguese, to the rest of the world, with the first stop in beautiful Lisbon. So Cape was also not anymore a color descriptor many years ago. As a student, a diamond student, I remember listening about the Cape series, about Cape diamonds, but the younger generation, we don't listen to them. We'd see them on books, but not anymore. And I didn't dive much into color grading, but the color grading systems came into action more than 70 years ago to put some order in color descriptors. So to make sure that color and the other characteristics of diamond are correctly communicated to the consumer. And so this is it. This was our webinar for today, and it matters. So I'm going to just move my eyes away a little bit from the camera so I can see some questions. And of course, I always choose the easy ones, never the difficult ones. Oh, Hansa Shash, I don't know if Hansa is a male or female, but please explain the difference between type 1 and type 2. It's not difficult. The scientists decided to classify diamonds according to the nitrogen impurities, okay? And when diamonds have nitrogen, and nitrogen, I mean, in the atmosphere, 80% is nitrogen, but not on the mantle. And when the diamonds have detectable nitrogen in infrared spectroscopy, it's a type 1 diamond. When they don't have nitrogen detectable in infrared spectroscopy, is called a type 2 diamond. And then in type 2, you have the type 2A and type 2B. Type 2A, you have nothing. You don't detect nothing in the infrared spectroscopy other than carbon and some defects or vacancies, but no other impurities. On type 2B, you have no nitrogen, of course, it's a type 2, but you have boron. Boron, which is another chemical element, can also go into the lattice of diamond. And type 2B diamonds typically have a blue color, as Eloise explained on her webinar a couple of weeks ago. Type 1s, you have two types, you have many types in type 1, but you have type 1A, which is basically 98% of all diamonds on the planet are type 1A, meaning that they have diamond, they have nitrogen, and nitrogens, you remember that carbons, they hate each other. They want to be apart from each other. But nitrogens, oh, nitrogens, they are very sociable. They love to be with each other. When diamonds are born in nature, nitrogen is incorporated into the crystal, isolated. And when nitrogen is isolated, it is said that it is a type 1B. And type 1Bs in nature are very rare. When you go to synthetic HPHT diamonds, type 1Bs are quite common. But you remember, carbons hate each other, but nitrogens, they are all for the love. So if they are on a diamond, a recently born diamond, and they are stuck on the crystal sit, and they see another nitrogens over there, they want to meet and to be close to the other nitrogen, but it takes a long time for them to join. But over the geological period of diamond inside the mantle, high temperature, high pressure, those nitrogens, they eventually start aggregating and they form pairs, they form trios, then they can be 4 nitrogens, and then they have empty space in the middle. So they aggregate in different ways. And when they aggregate, we say that they are type 1a. And then depending on the way they are aggregating, if they are like only on pairs, it's an A aggregate. If they have, then you have many aggregates. I don't want to complicate, but it has to do with the type of aggregation that you then define the type 1A and type 1B. Type 1B isolated, type 1A aggregated. Then you have type 1AA, type 1AB, type 1AAB. So I hope I replied to your question, and I try not to be very technical, but basically this is this explanation. Why is so popular consider Golconda as a mine? Why lots of people do this mistake? I wouldn't call it a mistake. I mean, it's hard to say that it is a mistake when you have a verbal tradition, because it's, I mean, you call turquoise to that mineral that is not from Turkey, right? And that's for sure. You have another situation, marcasite. Marcasite is a iron sulfide that was really popular. It's a metallic cluster mineral, a metallic cluster material that was really popular in the 1930s and 1940s in England. And actually, it's not marcasite, it's pyrite. But you don't call it pyrite. We still call them marcasite. Is it a mistake? Technically, yes. But I mean, this is a trade. We use trade names and we use romance. So I wouldn't call it a mistake to call it a Golconda mine. It's inaccurate. Not a mistake, because people read what books say, and sometimes when you read a book, you don't care to watch the sources and check if the source of the book is correct. And sometimes one author says something in one book and then it is replicated everywhere. Like the Braganza diamond, one author decided that the Braganza diamond was a topaz, and so the Braganza diamond is a topaz everywhere. And the Braganza diamond is not a topaz, it's a beryl. So there you go. So a mistake, I think we should not be so harsh on people. Oh, the difference between an allotrope and a polymorph. An allotrope is a polymorph when the polymorph is a single element mineral, when it is a native element. That's it. You call it just a different name because it's a polymorph, of course. Carbon has two polymorphs, which is diamond and graphite, but because it's only carbon is only one element, you call it allotrope. It's the same thing. But for instance, calcium carbonate, you have aragonite and calcite. You don't say that aragonite and calcite are allotropes of calcium carbonate. You say that they are polymorphs of calcium carbonate. That's the difference. So diamond and graphite are polymorphs of carbon. In a sense, yes, but it's more accurate to say that they are allotropes of carbon. Amorphous of carbon, it's rubbish, it's nothing. So allotrope, everyone, each and every one of you, you will remember the word allotrope. You will remember allotrope at least. So diamonds can form at depths up to 700 kilometers, yes, and even a bit more. So some diamonds can form in really great depths. It's absolutely, oh, I must, Graça. It's always Graça Rosas. Thank you, Gracinha. Thank you very much. She's my angel. Okay, now you are seeing, this is so embarrassing because I thought I was sharing the results and I was just talking to a machine. So in the first one, we've done this, allotrope. Diamonds can form up to 700 kilometers, yes. And usually they are formed not as, they are formed at 150 to 100 kilometers, but they can go even deeper. And that's really remarkable. That's why geologists, they love diamonds, because what they do with diamonds, they pick a diamond and they destroy it so that they can see what's inside. For instance, that mineral that some of you already know, which is bridgemanite, the most abundant mineral on the planet, bridgemanite. So The oldest diamond on record is, I had a few years, and so 500 million years old. It's much older. 1.5 billion years old. It's much older. It's 3.8. Actually, it's not 3.8. It's 3.5, 3.6. Doesn't matter. But it's about the same time of life on Earth. 4.6 is the age of the planet, so it couldn't be at the same time. So 4, and this was probably the most interesting takeaway of this webinar, was to discuss the word Golconda. And the Golconda is an old mine in India that only produced top quality diamonds. Still 70% of you said yes, but no, Golconda was not a diamond mine, was a citadel. But around Golconda, yes, we did have diamond fields, alluvial diamond fields. Kollur is one of the most famous ones. And from the Kollur, or the mining area, of course, some fantastic diamonds came, but also the others, the normal ones that flooded jewelry making in the 14th, 16th, 15th, 17th century, up until the discovery of Brazil. So not only high quality diamonds came from the Golconda area, that is not a mine. So the 5 and last one, D to Z color scale relates to colorless to near colorless in the following hues. So yellow, yes, brown as well, grays also, it's all of the above. So you can grade in the GIA standards, of course, because standards are not universal. But you can on the GIA standards, you grade D to Z if the perceptible color is in the yellow, gray, or brown hue. The others, they are taken care of in a different way. So basically, this was it. You did very well. Congratulations again. So I'm going to close the show. Thank you very much again, everyone, for having attended this session. And so stay safe, stay connected, stay strong, and have a great weekend, and stay at home. Okay, bye-bye.